Afternoon, students. Am I audible to you? Just a second. Yeah, good afternoon. So, am I audible to you? Please reply. Am I audible and is the screen visible to you? Okay. So, finally, I welcome you all to the last lecture of this engineering mathematics. And then in this lecture, we basically complete this, Laplace transforms, and we'll talk about the basics of Fourier series, and then we'll wind up the sessions. So let us continue here. So if you recollect, in the morning class, we stopped to find at the point in finding Laplace transform of e power at, correct? And the Laplace transform of e power at is 1 by s minus a is what we got next. So Laplace transform of sine at and Laplace transform of cosine at, cos at is equal to, so could you tell me some values for this? So can someone tell me about this? Sin 80 and cos 80, a by s square plus a square, for this or for this? A is for sin or cos? For sin, correct? So a by s square plus a square divided by s by a square plus s square, or s square plus a square. So many times, in interviews, they'll ask you to derive this Laplace transform of sin 80, because the sine and cosine functions are the common inputs which we put even in any branch of engineering, like generally sine inputs and cos inputs, because the smoothness of the curve is governed. So let us try to derive this once. We know e power I at is equal to cos 80 plus I sin 80, correct? This is what we have seen in complex calculus, correct? So cos 80 plus I sin 80. So now if I find this Laplace of e power I at, this is equal to integral 0 to infinity e power minus st into e power I at dt. This is what we have, correct? So integral 0 to infinity e power minus of s minus ia into t dt. This is what we have, because if I write this a power m into a power n format, I have e power minus st plus e power i8, e power minus st plus iat. So if I take minus sign common, I'll have s minus ia. Okay, so this implies Laplace transform of e power iat is equal to, see here, if you evaluate this integral, we have e power minus of s minus ia into t divided by s minus of s minus ia, correct? So within the limits 0 to infinity. So now if you substitute this, if you take this minus 1 by s minus ia common out, first of all, from the substitution of limits, because this minus sign can be taken out, and this s minus ia which is here can also be taken out into the denominator. Now if you put this limits t into some infinity, so e power minus infinity term will give you 0, and this is minus 1. So this is 1 by s minus ia. So this is the Laplace transform of e power iat. But if you rationalize this, s plus ia divided by s plus ia, so this is equal to, numerator is 1 into s plus ia, so this is s plus I into a divided by, so this is of the form a minus b into a plus b, so for which we have a square minus b square format. So if this is a minus b into a plus b form, then a square minus b square, which is ia whole square, and minus into I square will give you plus actually. So this is s plus I by, I into a divided by s square plus a square. So one thing that we got here is Laplace transform of this e power I at, since we know e power I theta can be written as cos theta plus I sin theta, this e power I at can be written as cos 80 plus I into sin 80. Now this, if you split this at this plus sign, s by s square plus a square plus I into a by s square plus a square. This is what we have, correct? So now this implies, so since this is a Laplace transform, and Laplace transform is nothing but an integration, you can split this integration at all plus and minus signs. So if you see Laplace transform of cos 80 plus this I is a numerical constant, so I into Laplace of sin 80 is equal to s by s square plus a square plus I into a by s square plus a square. So now if you compare these two equations, The real parts, if two complex numbers are equal, we know the real part should be same and also the complex part should be same. So if you see, this Laplace of cos AT is s by s square plus a square, which we written here. Laplace of cos AT is s by a square plus s square, and Laplace of sin AT is a by s square plus a square, which is the real part of, I mean the imaginary part of this. So this is how these two are deduced from this particular analysis. Okay, I told you this because in many interviews, you know, this sine and cosine function are very common functions. You know, they have the specialty for smoothness. They don't have any jerks like mod x function and all. For mod x, here suppose if one value is decreasing, suddenly it should increase again. Means here the rate of acceleration should be very high. But for sine and cos, we have some smoothness. So these curves are generally used for cycloidal motions and all. So if you are doing control systems, then this could be of very much use to you. So sin AT Laplace transform is a by s square plus a square, and cos AT is s by a square plus s square. Okay. Next, could you tell me what is Laplace of sin h AT? Sin h AT, you know, sin h hyperbolic of this function is nothing but e power x minus e power minus x divided by 2. So if you take 1 by 2 common, you have Laplace of e power AT minus Laplace of e power minus AT. And we know Laplace transform of e power AT is 1 by s minus a minus the Laplace transform of e power minus AT is 1 by s minus of minus a, because this minus a itself is the constant here. So 1 by 2 into 1 by s minus a minus 1 by s plus a. So if you take LCM, 1 by 2 into, so if you take LCM, s plus a minus s minus a, so this is 2a, which is here, divided by a minus b into a plus b is again s square minus a square. So 2 gets cancelled. We have a by s square minus a square as Laplace transform of sine hyperbolic of AT. Okay, so this is what we have. Similarly, if you calculate for cos, can you tell me what you will get? If you calculate for cos, Laplace of cos h AT, if you calculate, what you will be getting? See, it's a very easy thing to tell this. Correct? S by a square, s square minus a square, because for cos h AT, everything remains same, but instead of minus, there comes a plus here. So plus, so when you, here it comes plus. So when you take LCM, this a gets cancelled instead of s getting cancelled, and even s will be left over in the numerator. So s by s square minus a square. This is what we have for Laplace of sin h AT and cos h AT. Okay. So now, as we know, there is linear property in Laplace transforms, which means if you have two functions, means for example, you can write maybe properties of Laplace transforms. Properties of Laplace transforms. So if you write this first property, you can have something like linear property. And what does this linear property tells us? Suppose if you have a combination of functions with a linear multiplication of scalars, means a into f of t plus b into g of t and so on, things like this, then this can be split as, you know, this Laplace operator, this L stands for Laplace operator, which is integral 0 to infinity e power minus st into this function a into f of t plus b into g of t. And since you know integration can be split at all plus and minus signs, this can be written as a times of Laplace transform of f of t plus b times of Laplace transform of g of t. This is what we can write here. Okay. Second, we call this as first shifting property. First shifting property. And what does this first shifting property tells us? You know, generally when you calculate Laplace transform of any function in time domain, we'll be getting the answers in S domain, correct? For example, if you see this is a time domain, means we have the independent variable as t, and the final answer that you'll be getting is in terms of s. So which means if Laplace transform of f of t is equal to f bar of s, this is some function. Maybe you can write small f or capital F, doesn't matter. Let us write small f. So this f of t and f bar of s are not same, because you see I have put a bar here, so which means these both are two different functions. For example, if you see this function is sin h AT and this function is a by s square minus a square. So these two are two different functions, but my main intention is to tell you that this answer function which I am writing here is completely dependent upon s, and of course some constants. Okay, but no t. then Laplace transform of e power at into f of t is equal to f bar of s minus a. This is what we have. Correct? Means this is called shifting, because whenever you are shifting this e power minus st with a multiplication of e power at, instead of f bar of s, it will be f bar of s minus a. Means if you plot s in the s domain, the s gets shifted by this a on the s axis. Okay. So now if you want me to show this, it's a very simple thing. Just a 2 minutes we can spend on this. So given Laplace of f of t is equal to f bar of s. Correct? So see here, if Laplace of f of t is equal to f bar of s, then this implies, Laplace of e power at into f of t is equal to integral 0 to infinity e power minus st into e power at into f of t dt. This is what we have. Correct? Now integral 0 to infinity e power minus of s minus a into t into f of t dt. Now if I make a substitution, let s minus a is equal to, who here is on short line? Nagasai. So let us suppose, okay, s is already utilized, so let us take v. S minus a is equal to v. So then this implies your a, s minus a is equal to v. If you take this s minus a is equal to v, then if you go for upper limits, let me take this as, see here, integral 0 to infinity e power minus st into e power at into f of t dt. So if you take this s minus a is equal to r, we have something like, if s minus a is equal to, okay, let us take r. So integral 0 to infinity e power minus rt into f of t dt. Now tell me one thing, if you have integral 0 to infinity e power minus st into f of t, which is the Laplace transform of this function f of t is f bar of s, means if you have s here, now if this expression, if it says integral 0 to infinity e power minus rt into f of t dt, what it should give me? All of you, please tell me. If this expression is equal to f bar of s, now what this expression should give me? Integral 0 to infinity e power minus rt into f of t dt, where r is again a constant, because s and a are constants here. So please tell me what it should give me. All of you, I want all of you to respond. You have some 47 are on live, so respond. F bar of r, and the assumption that we made for r is f bar of r value is s minus a, and this implies Laplace transform of e power at into f of t dt, I mean f of t, okay, is equal to f bar of s minus a. So this is what we call as first shifting property. See, Maheshwar, I am showing you something. I just made this constant as a single term, that's it. I didn't use any t here, so variable of integration is not changing here. Okay, yes, variable of integration is not changing. Okay, Maheshwar. So next we'll go for one more thing, which is called change of scale property. Change of scale property. Okay, so if you have this, if f of t means Laplace of f of t is equal to some function f bar of s, then today is the last class. So then Laplace of f of at means, instead of t, if you are substituting at, means change of scale, means instead of t we are putting some linear multiple of t. Okay, then we know the dimension increases. So Laplace of f of at is 1 by a into f bar of s by a. This is what you have. Okay, so this also, if you want, you can prove easily. You can take at is equal to some v, then you will be getting this term actually. Okay, so please try to prove this. It's simple really. I'm not proving it anyhow at this instant. Okay, fine. So see here, next we go for multiplication by t power n. Multiplication by t power n. 1 by a into f bar of s by a. This is what we have. So see here, multiplication by t power n means if Laplace of f of t is equal to f bar of s, then Laplace of t power n into f bar of f, f of t, means if you are multiplying this with f of t is equal to, then this value is equal to -1 whole power n into d nth derivative with respect to n s into of f bar of s. So this is what we have. Means if you know that Laplace transform of f of t is f bar of s, yeah, of course, if you want, you can put modulus here, no issues. So see here, Laplace of t power n into f of t is equal to -1 whole power n into d nth derivative of this function with respect to s, f bar of s. Okay, so this is what we have. For example, if you see Laplace of sin t is equal to how much? Just now we had used s by a square plus, okay, let me write sin at, for example. Laplace of sin at is equal to a by s square plus a square. This is what we have. So if you want Laplace of t into sin at, then you know we have one multiplication of t here, so n value is 1. So -1 whole power 1 into d by ds of this function a by s square plus a square. And you know, yes, a is a constant, so a, if you bring it out, minus a into d by ds of 1 by s square plus a square. So you know, d by ds of s square plus a square whole power -1. Correct? So this is minus a into -1 into s square plus a square, s square plus a square whole power -2 into the inner derivative of this function with respect to s is 2s. So if you see, you can cancel this 1 and 1. So 2as divided by s square plus a square whole square. This is how you will be finding the Laplace of t into sin at basically. So if a value is 1, your answers get simplified a bit. So Laplace of e power at into, t into sin at. Okay, t into sin at. This is what we have here. 2as divided by s square plus a square whole square. Okay, so like this, generally practically applying the definition for this, like integral 0 to infinity e power minus st into t into sin at dt is difficult to calculate practically. So when you have this multiplication by t power n formulation, you can apply this right away and you can differentiate this function once, for which you can get the answer. But practically, just by going with the definition, it takes a lot of time for us to evaluate. Okay, so clear to all of you? Okay, so now I'm going ahead. Division by t means like how we have multiplication with t power n. Similarly, if we have division by t, then let us see. If Laplace transform of f of t is equal to f bar of s, then Laplace of f of t by t means if you have the function with a division with t, then you know this can be written as integral s to infinity f bar of s ds. This is what we have, integral s to infinity f bar of s ds for this. So you can calculate the things now. So for example, if you have Laplace of sin t is equal to, just now we have seen how much is the answer, sin at, for example. Okay, so first of all, let us calculate for sin t. First of all, so Laplace of sin t is equal to how much? 1 by s square plus 1 square, correct? Because Laplace of sin at is a by s square plus a square, so 1 by s square plus 1. So now if you put Laplace of sin t by t, Laplace of sin t by t, now as per this result, when you have division by t, you know it's integral s to infinity f bar of s 1 by s square plus 1 ds, and you know the integration of this is 1 by s square plus 1 ds is tan inverse s within the limits s to infinity. So this value is equal to, when you substitute infinity, tan inverse of infinity is pi by 2 minus tan inverse of s. This is what we have. So we have Laplace transform of sin t by t is equal to, which is integral 0 to infinity e power minus st into sin t by t dt is equal to pi by 2 minus tan inverse of s. And this result is really important to us because there is one particular integral in indefinite integration which is really difficult to evaluate using standard methods of this basic calculus. For example, if you see integral 0 to infinity sin x by x dx. If you don't know this result, calculating this integral is really difficult, and this is a previous gate question once. I don't know of which of the branches, I didn't remember exactly, but this is a previous gate question. Okay, the value of this. So integral 0 to infinity sin x by x dx. So now if you put s is equal to 0 in this equation, basically, so if you put s is equal to 0 in this equation, integral 0 to infinity e power minus 0 into t. So this value is 1. So 1 into sin t by t dt, which means you have this. Of course, if I put t here in place of x, integration remains the same. So when you put s is equal to 0, even here you need to put s is equal to 0, and tan inverse of 0 is 0. So the answer for this is pi by 2. Okay, and this value is really important for us. Integral 0 to infinity sin x by x dx. Okay, so this is pi by 2. And that's the value of integral 0 to Laplace transform of sin t by t, which is pi by 2 minus tan inverse of s. Okay, so for any given s value, you can calculate this value of pi by 2. Okay, and this integral you can put a star if needed. It's really important because in exam, if you don't know these Laplace transforms, it's really difficult to calculate this integral using manual methods. And of course, you can't apply numerical integration techniques because this is infinity, means x is changing from 0 to infinity. So number of intervals you need to split is out of your hands, so you can't do. Okay, clear so far? One thing, please don't mind, I'm not giving proofs of all these things because proofs are with respect to mathematics, proofs of these Laplace transforms and all is not of much importance to us. Okay, at this context. So clear to all of you? Did you all understand till this? And please make a note, this result is really important. Okay, all of you, I want all of you to respond. I want some 48. So please respond. Okay, so now we'll continue. Similarly, if you have now change of scale property, if you apply change of scale property, if this is the function, we have pi by 2 minus tan inverse of s by a. So what do we have? If suppose if I have sin at by t, if I have sin at by t, sin at divided by at, for example, what could I have there? What I'm asking you is Laplace of sin at by t, this value, which means integral 0 to infinity e power minus st into sin, at divided by t. So could you tell something for me to this value? I'll give you time for 2 minutes. Can you calculate and tell me? I told you change of scale property, so try to use that change of scale property because you know formula for Laplace of sin t by t. Just now we have seen pi by 2 minus tan inverse s, correct? So in place of f of t, if you take this complete function sin t by t as f of t, then what could be the answer? Pi by 2 minus tan inverse of s by a. Could it be something more than that? Yes, 1 by a into, correct. Vamsi. So if you see, this can be written as a into one more a here, correct? Because this a is a constant and this can be cancelled out. So for this, you can apply change of scale property. So now if you apply change of scale property to this is equal to a into Laplace of sin at by t. See, for sin t by t, you have this. So a into pi by 2 minus. Okay, so Laplace transform of this with respect to this particular thing is pi by 2 minus tan inverse of s by a. I think these a's are not present here. If you write one a, you can write one more a here as well. That could be fine. Okay, so Laplace of sin at by at is equal to 1 by a into pi by 2 minus tan inverse of S by A. Okay. So this is the result which we have. Okay, so basically if you have any function, you can try to calculate the Laplace transform straight away from the definition, from the kernel function basically. So if it's not possible, if you have some multiplications of t, or if you have some e power at's and all, we have seen enough properties like how to calculate Laplace transforms of different functions. Okay, so basically in exam, as per mathematics part is concerned, they'll ask you, like they'll give you certain function and they'll ask you how to, what's the Laplace transform of that particular function. Okay, this is what they ask you in exam many times. And this integral is important because sometimes people give this question and people feel that this is from calculus and they'll start substituting the things and working out, but things won't go fine at that moment. Okay, so this is how the answer is pi by 2 for this integral. Next, so now we have seen finite number of methods to calculate Laplace transforms of different functions. Like basically if there is a function, if there is some e power at multiplication to that function, or in place of t, if there is a into t, if there is some multiplication of t, t power n to that function, and then if the function is divided by 1t, what to do? We have seen all this. So now we will go for something called inverse Laplace transforms. Okay, so inverse Laplace transforms. Inverse Laplace transforms. So in inverse Laplace transforms, we say if Laplace transform of f of t is equal to f of s, f bar of s, of course this Laplace transform exists, then we say f of t is equal to L inverse. This L inverse indicates inverse Laplace operator. So L inverse of, did I write tan of s by a here? Tan inverse only, no? Yeah. Okay, so see here, Laplace inverse of f bar of s. So if you follow this example, we have first point L inverse of n factorial divided by s power n plus 1. Of course, n is equal to 0, 1, 2, 3 and on. What could be the answer for this? In brackets, n is equal to 0, 1, 2, 3 and so on. In morning class, I have derived this formulation, correct? So Laplace transform of some function is equal to n factorial divided by s power n plus 1. And what is this? T power n. Correct? We derived in today morning. See, if you remember, if you don't remember, we'll go to this part. So Laplace transform of t power n is basically, after all this analysis, I showed you this value is n factorial divided by s power n plus 1. Correct? So that a value, if Laplace of t power n is n factorial divided by s power n plus 1, then the Laplace inverse of this function n factorial divided by s power n plus 1 is t power n, which is defined here. Next. So similarly, Laplace inverse of a by s square minus or s square plus a square. What could be the answer for this? Laplace inverse of a by s square plus a square. All of you. Sin at. Sin at. Next. If you have Laplace inverse of s by a square plus s square, this is also same as, what does this give us? Cos at, correct? So cos at. Similarly, if I write Laplace of, if I write Laplace of a by s minus a whole square plus a square, if I write this, can you tell me what's the Laplace, what's the function for which this is a Laplace transform? See, basically this is the function where if you put s minus a in terms of a, or else for making the things clear, let me put s minus b so that you won't get confused. So if I write this, okay, so this is e power bt into sin at. Yeah, before when I write a here, your answers are correct. Suma and Prem Kumar, Alekia, Pen and all. Okay, so see here. Similarly, if I write Laplace of, L inverse of s minus b divided by s minus b whole square plus a square. If I have this as a Laplace inverse function, then what could be the answer for this? Can some of you tell any answer for this? Laplace inverse of s minus b divided by s minus b whole square plus a square. E power bt into cos at. Next, if I ask you Laplace inverse of 1 by b into 1 by b into a by s square. Okay, let me simplify the questions first. Let us not go for the complicated parts straight away. So 1 by b into s. Can you tell me for what function this is the Laplace transform? 1 by bs. 1 by b. Correct? Because Laplace transform of this 1 by b is 1 by b can be written as a constant into Laplace transform of 1, which is 1 by s. So we have all these things. You are welcome, Mitlesh. Where are you, Mitlesh? Where are you from, Mitlesh? From where are you listening this class? Mitlesh Gupta. Names are a bit different, so I'm asking. Okay. So see here. So this is what we have, and similarly we can work out different things based on our knowledge. So sometimes there comes some functions here which we can't tell directly, like how we are telling here. So to sort out such kind of questions, we have something called partial differentiations and all. Okay, I mean partial fractions and all. Okay, so let us see here. Laplace inverse of s square divided by s square plus a square into s square plus b square. Okay, so please try to tell this. No need to convert this into partial fractions. You can directly use whatever the method you have or you are acquainted with. This is just pure basic algebra that we do in mathematics. Okay. So please tell me. I'll wait for your answers. So I hope we finished the syllabus in a good way. Like I feel that these lectures are useful to you at some point, genuinely speaking. Meanwhile, since today is the last class for mathematics, I counted on a bulk total how many views I got for the videos and for all these things. I'm telling you honestly, yesterday night I was counting in our system. The total views I got is 47,800 plus for all these videos. Okay, so next total number of watch minutes is 6,04,000 plus. I don't remember these 3 digits because we generally measure them in k minutes. So 600 plus k minutes. Better write k here and plus here. Which means I hope students are making use of these things. And these are exclusively for maths. I didn't count for thermodynamics again. These are only for maths. Okay. So 47,800 plus views is, I think, people are making some good use of it. Anyhow, this content is for free and we are not charging anything for this. If you feel that this content is good, you can share to your friends as well. Okay, because since this is of free and we are not charging anything for this. By the way, what's the answer for this? Suma? 1. Okay. When everyone is busy talking, she solved it. Okay. So 1 by b square minus a square into sin at by a minus sin bt divided by b. Okay, so let me check. So this is Laplace inverse of, see carefully. Can we write this as 1 by, look, Laplace inverse of this function s square divided by s square plus a square. When you have things like this, like x by x plus some constant, like for example, x by x plus c1 into x plus c2, things like this. you can split it into partial fractions, or if you don't like to split into partial fractions, you can arrange the terms in such a way. See here, if I write 1 by s square plus a square minus 1 by s square plus b square, what do I have here? Please tell me, what do I have here? Or else if you want, you can split to Laplace, partial fractions, better. Okay, so if you split to partial fractions, what could come here? Divided by s square plus a square and s square plus b square. So please tell me, what are the coefficients here? For the first coefficient, what is the first coefficient? Of course, 1 by b square minus a square term will come, definitely. So into 1 by b square minus a square. Okay, next 1 by b square minus a square. Okay, next here, what are the terms that comes here? Calculate partial fractions, it's very simple. So you have s square term here, s square by a square, s square by b square. Here it's 1. Okay, what about here? If you calculate into partial fractions, minus 1. Correct? Yes or no? No, correct? Because if you cancel this s square which is in the numerator gets cancelled off. Yes or no? So for the simplicity, let us make one thing. Let us make 1 here. First of all, since we are struggling to deal this, then I hope this thing could be correct. Okay. Since we are feeling difficulty in finding partial fractions, let us reduce this question to 1 by s square plus a square. Of course, for s square here, we have another plan. We'll do. So see here, this is what we'll be getting. Correct? If you take LCM, b square plus s square minus of s square plus a square. So s square gets cancelled, and the numerator, which is with b square minus s square, will be b square minus a square will be getting here. Okay. There is something called convolution theorem. There I'll tell you with s square here. Okay. No issues. So this is equal to L inverse of this. And if you see, this Laplace inverse of 1 by s square plus a square can be written as 1 by a into a by s square plus a square minus 1 by b into b by s square plus b square into 1 by b square minus a square. So this is equal to this 1 by b square minus a square. If you write it in the front, you can have this 1 by a is a constant. So Laplace inverse of a by sine of a by s square plus a square is sine at minus 1 by b into sine bt. This is what you have. So this is equal to 1 by b square minus a square into b sine at minus a sine bt divided by ab. Okay, just taking LCM here and getting this ab term. Okay. Clear to all of you? Okay, so now we'll go for something called convolution theorem. Convolution theorem. If Laplace transform of f of t, or you can write Laplace inverse of basically f bar of s is equal to f of t, and Laplace inverse of g bar of s is equal to g of t. If we have two functions in this way such that both these Laplace transforms are f bar of s and g bar of s, then this implies Laplace inverse of f bar of s into g bar of s. this can be written as integral 0 to t f of u into g of t minus u du. This is what we can write, and we can calculate this integral basically to evaluate the Laplace transform of two functions. For example, if you see this function, they can be written as 1 by s square plus a square into 1 by s square plus b square. So this is nothing but sin at by a minus sin bt by b. We can calculate using this integral. So now we'll see the value of this. Laplace inverse of s square divided by s square plus a square into s square plus b square. Anyhow, I'll also calculate partial fractions and I'll show you this. No issue. But first, I want to show you this using convolution theorem. So L inverse of this can be written as s by s square plus a square into s by s square plus b square. So basically, Laplace inverse of these two functions, where this is the Laplace inverse of the Laplace inverse of this term will be cos at, and the Laplace inverse of this term will be cos bt. So now if you apply this convolution theorem, so see here, as per convolution theorem, integral 0 to t, this function f of t, so cos at into cos b of, cos au, sorry, this is cos au into cos b of t minus u dt. Now you have product of two functions, so we can write this as 1 by 2 into integral 0 to t 2 cos au into cos b of t minus u dt. Correct? This is what you have. So now this is equal to 1 by 2 into, see, this is 2 cos a cos b format. Correct? 2 cos a cos b can be always written as cos a plus b is equal to cos a cos b minus sin a sin b. Similarly, cos a minus b is equal to cos a cos b plus sin a sin b. So if you add these two things, this gets cancelled. This gets cancelled, and 2 cos a cos b is equal to, we have cos a plus b plus cos a minus b. So this implies 2 times of cos au can be treated as one variable, for example capital A. This b into t minus u can be treated as another variable, which is b. So this method which is here, we can write it as this, and the the integration of this cos is minus sign, and integration of this, integration of cos is sign, integration of this cos is also sign here. Sorry, here it's du because variable is u. Correct? Du and du, because the main function we are putting is u. What did I write here? Du. Correct? Okay. So this is du. So now if you use this analysis, so 2 cos a cos b can be written as integral 0 to t cos a plus b. So cos a plus b is au plus b into t minus u plus cos of au minus b of t minus u. This is what you have to this du. So if you apply this, you can calculate half into integral 0 to t. Okay, let us retain this as integral 0 to t. So cos of, see here, a minus 1 into u plus bt plus cos of a plus 1 into u minus bt du on a total basis. Correct? So now you can integrate this. You have cos function, and this is the inner derivative, so divided by a minus 1, a plus 1 and all. So you can calculate the values. So please try to calculate what's the value here. Here it's a minus b, correct? Here also it's a plus b. Correct, because there is b multiplication. Okay, Monica, thank you. Here it's a minus b because this b is in multiplication to this minus u, and also here this u is in multiplication, this b is in multiplication to that minus u. Okay, so this is what we have. 1 by b square minus a square into b sin at minus a sin bt. So let me check. 1 by 2 into Integration of this. Integration of cos is sine. So sine of a minus b into u plus bt, and whenever you are integrating with respect to u, this a minus b can be written here. Similarly here, plus cos, sine plus sine of a plus b into u minus bt divided by a plus b within the limits 0 to t. You can calculate this value. Whatever is there, you can put. So a minus bt plus bt gets cancelled. So you have sine at divided by a minus b. So 1 by 2 into, if you put t here in place of u, upper limit, this a minus bt plus bt. So bt will get cancelled. So you can write sine a t divided by a minus b plus, again if you put t here, this bt will be again gets cancelled. So sine at divided by a plus b minus, if you put 0 here in place of u, you have sine bt divided by a minus b and plus sine, again if you put 0, sine minus bt, which is minus sine bt. So you can put minus sine bt here divided by a plus b. So now you can simplify these things for a minus b and a plus b coefficients. You'll be getting something like, if I think I'm correct, I'll be getting 1 by b square minus a square into b sine at, yes, minus a sine bt. This is what I'll be getting as a Laplace transform. Laplace inverse of this function is this. Okay, correct, Shankar. This is what we'll be getting if you simplify here. See, you can take sin at minus sin bt common, then you'll be having 1 by a minus b minus 1 by a plus b. So if you simplify, you will be getting this value. Okay. So now, if you have differentiations, we'll see. Laplace of, if you have derivatives, basically, like f of f nth derivative of t, means like basically Laplace transform of some derivative of a dependent variable with respect to t. If you have something like this, then this is s power n into f bar of s minus s power n minus 1 into f of 0 minus s power n minus 2 into f double dash of 0 and so on, minus f nth derivative at 0. This is what you will be having. Okay, and where you can see this f is this f and this f bar is the Laplace transform of this f, where f bar of s is equal to Laplace of f of t. So if Laplace of this f of t is this, then nth derivative of this will be, nth derivative of this function f of t is written in this format, where this is s power n into f bar of s minus and all. So now in control systems, what happens when you are writing transfer functions for a given input and output, we assume all these initial conditions to be zeros. Okay, I told you morning, the transfer function is the ratio of Laplace transform of output to the input while assuming all the initial conditions are 0. So if you consider this, these are the initial conditions at time t is equal to 0 basically. So all these are 0 and we consider only this part, which is s power n into Laplace inverse of, s power n of f bar of s. Okay, f dash of 0, acha, this is f dash of 0 then. Okay, basically this is what I need to say, f of 0 minus s power n minus 2 into f dash of 0 and so on. Okay, one extra dash was put here, but that's not correct. Okay, so all these are minus signs. There is no plus and minus all time. All these are minus signs apart from this. Clear? Okay. Next. So we'll try to solve one differential equation. Okay. Solve y triple dash basically, or else let us put y double dash. Fine. So y double dash plus 2y dash minus y. Okay, let me see the question once. I hope that I got the question to make you to solve here. So yeah, today I got some cheat with me to tell you. Okay, so this is the question that we'll be solving. Solve y triple dash plus 2y double dash minus y dash minus 2y is equal to e power t. Correct? E power t. No, this is equal to 0 actually. 0. Okay. Given y of 0 is equal to y dash of 0 is equal to 0. Okay. And y double dash of 0 is equal to 6. These are the conditions we have. Okay. So this is what the question we have. Solve y triple dash plus 2y double dash minus y dash minus 2y is equal to 0. So these are the given values. So if you apply Laplace transform on both sides of this equation, see here. Laplace inverse of y triple dash plus 2y dash minus y dash minus 2y is equal to Laplace. If you apply Laplace transform, Laplace of this is equal to Laplace of 0. And you know Laplace of 0 is anyhow 0. So Laplace of this function y triple dash is, if you see, s cube into f bar of s minus s square into f of 0 minus s into f dash of 0 minus f double dash of 0 plus 2 times of Laplace of y double dash. So y double dash is s square into f bar of s minus s into f of 0 minus f dash of 0. Next, minus y dash. So Laplace of y dash is s into f bar of s minus f of 0. Next, Laplace minus 2 into Laplace of y. Laplace of y is nothing but, if y is some function f of t which is satisfying this condition, then this is f bar of s is equal to 0. This is what we have. Correct? Now, if you see carefully, all these values are given. Y of 0 is equal to 0, y dash of 0 is also equal to 0, which means you can write this is 0. Okay, since we are considering this as f is equal to y, so this two terms, this term and this are zeros. Correct? So this is the question. Solve this differential equation with these are the initial conditions. Okay, so we are solving this differential equation with the help of Laplace transforms. Okay, so if you solve this differential equation with the help of Laplace transforms, then you have things like this. So now this implies Laplace of, see carefully, I mean this Laplace transform we have already utilized. So we have one expression. Let us see that. S cube into f bar of s. S cube into f bar of s. Next. S cube into f bar of s minus, again if you see, minus f double dash of 0 is here. So f double dash of 0 means basically if you are taking this Laplace of f of t is equal to f bar of s, we can write Laplace of y of t is equal to y bar of s. So please don't get confused with the terminologies. So we can put s cube into f bar of s minus f double dash of 0. It's given 6. So minus 6. Next, plus 2 times s square into f bar of s plus 2 times s square into f bar of s Again, that's it. These two terms are zeros. Minus s into f bar of s minus s into f bar of s. And what do we have? Still minus 2 times of f bar of s. Minus 2 times of f bar of s is equal to 0. This is what we have. Correct? So now, if you take this f bar of s common, f bar of s into s cube plus 2s square minus s minus 2 into, okay, is equal to 6. So this implies f bar of s is equal to 6 by s cube plus 2s square minus s minus 2. This is what we have. And so if you want, if this is f bar of s, and if you want this y of t, okay, so see here, f bar of s is equal to 6 by s cube plus 2s square minus s minus 2. So see here carefully, this f bar of s can be written as 6 by, if you factorize this, see, I told you sum of the coefficients 1 plus 2, 3, 3 minus 1, 2, 2 minus 2, 0. So if sum of the roots is, if sum of the coefficients is 0, then 1 is definitely one root of this equation. So into. So if you factorize, since you know one root, 1, s is equal to 1 with the Horner's method, 1, 2, minus 1, minus 2. So 0, 1, 1, 3, 3, 2, 2, 0. So s minus 1 into s square plus 3s plus 2. And if you see, s minus 1 into s plus 1 into s plus 2. This is what you have. Okay. So now, s minus 1 into s plus 1 into s plus 2. So now, if you apply this partial fractions here, 6 if you take as a constant, then s minus 1 plus some coefficient into s plus 1 plus some coefficient into s plus 2. So find out the coefficients here, constants. What are the constants you have here? So if you want the coefficient of s is equal to 1, put s is equal to 1 here. So 1 by 2 into 3, 1 by 6. So this is 1 by 6. Next, if you want coefficient of s plus 1, put s is equal to minus 1 in the complete equation. So minus 1 into minus 1, this is minus 2. Minus 2 into 1. Minus 2 into 1 is this minus 2. So 1 by minus 2 here. So 1 by minus 2 is minus 1 by 2, which is here. Next, if you want coefficient of s plus 2, then close this, put s is equal to minus 2, minus 3 into minus 1. Minus 3 into minus 1 is plus 3, and this is 1 by 3. And if you see, this 6 gets cancelled, so 1 by s minus 1 plus 2 gets cancelled, so this is minus 3 by s plus 1, and 6 gets cancelled 2 times, so 2 by s plus 2. This is what we have. So f bar of s is equal to 1 by s minus 1 minus 3 by s plus 1 plus 2 by s plus 2. Coefficient of s minus 1 is 1. Yes, 1 by s minus 1. See, I have taken the 6 common. Okay. See, if you don't take this 6 common, you can get directly 1 here itself. Okay. So 1 by s minus 1 minus 3 by s plus 1 plus 2 by s plus 2. Okay. So see here, if this is f bar of s, then what is, if you apply Laplace inverse to all these functions, this implies f of t is equal to, now this 1 by s minus 1, Laplace of 1 by s minus 1 is how much? We have seen Laplace of e power at is equal to 1 by s minus a, correct? So if you have a is equal to 1, the value of this is e power t. So f of t is equal to e power t. Next, minus 3 times of 1 by s plus 1. If you put a is equal to minus 1, you will be getting 1 by s plus 1. So this is e power minus t plus 2 times of 1 by s plus 2. This is nothing but e power minus 2t. This is what the differential equation we will be getting. I mean the solution of the differential equation. Okay. E power minus t plus 2 into e power minus 2t minus 3 into e power minus t. Okay. This is what we will be getting here as the solution by applying Laplace inverse of this. Here I have done complete question in terms of f. Basically you can assume f table derivative plus 2 times of f double derivative and all. Actually here I could have written s cube into y bar of s and all these things. But if you want, you can change this a bit. Instead of y's, you can put f. Okay, so if you apply f triple dash minus 2 times of f double dash minus f double dash is equal to 0, given f of 0 is equal to f dash of 0 is equal to f double dash of 0 is equal to 6. F triple dash minus f dash minus y is equal to, here you should have f then minus f is equal to L of 0. Then this is how things get matched. So you can see this is the solution of the Laplace equation, which satisfies the given conditions as well. Okay, you can calculate second derivative, and if you put 0, you will be getting 6. Yeah, you'll get the same thing. Okay, even if you solve using higher order differential equations for third order derivatives, you'll get the same thing again. Okay, so this is where we would like to end Laplace transforms. So basically, depends on the question. Basically, okay, if you have, normally in BTech exams they'll give you solve using this Laplace transforms, but in GATE exam you can always go for higher order differential equations. Okay, because this question, if you solve using higher order differential equations, it would come much easier. Okay, because finding the Laplace transforms. But in BTech exams, since even BTech studying students will watch these videos, I am telling how Laplace transforms can be applied in getting a solution for a differential equation of a higher order generally. Okay. And of course, if you see, I am dealing a simple case, homogeneous equation. On the right hand side, the coefficient is 0. Okay. Clear to all of you? I thought of discussing one question, so I got a cheat with me today to write this question. Fine. So is that okay? So basically in exam, people don't ask questions to this extent even. Of course, ESE and TRIPLE people, like anyhow you are familiar with your transform theory for the course of signals and systems, but generally for mechanical and civil branches, mechanical civil are the main interests why I am teaching this Laplace transforms here, because anyhow for ESE and TRIPLE you will be having signals and systems and your concerned faculty will teach you that. But coming to our GATE syllabus in mathematics, either they'll ask you the Laplace transform of some function, or they'll ask you, basically some Laplace inverse of some other functions, but not beyond that. Okay. But this question, integral 0 to infinity sin x by x dx, was asked many times. Okay. So you need to take care, because in analytical methods, evaluating that integral 0 to infinity sin x by x dx is not that easy. Okay. And also you can't apply this, numerical integration techniques, because x is changing from 0 to infinity. To how many intervals you will split? Okay, so numerical integrations also doesn't give a better value. Okay, so now we'll start Fourier series within short time. I'll just give you introduction, like how to calculate the Fourier series expansion of any given function, and we'll end the course. Okay, so Fourier series, if f of x is any function defined in the interval alpha to alpha plus 2c, where c is a constant basically. Okay, Fourier transforms and Z transforms I am not going to deal in this course, so because there are not much common parts to all other branches, so we are not dealing that. Okay, so I'll just give you the introduction of Fourier series and then we'll end up this session. So see here, if f of x is any function defined in alpha to alpha plus 2c, then the power series expansion, or you can write the Fourier series expansion basically. Then the Fourier series expansion of f of x in alpha less than x less than alpha plus 2c is given by f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity f of x into cos, you can write sigma n is equal to 1 to infinity an into cos n pi x by c plus sigma n is equal to 1 to infinity vn into sin n pi x by c. This is the general Fourier series expansion of any given function within the limits of this. And yes, to apply Fourier series or to evaluate Fourier series expansion of a function, the function has to satisfy some conditions, and these are called Distillate conditions, which we will see now. Okay, there are something called Distillate conditions, which we will see now, for which any function should satisfy these Distillate conditions so that it can be expanded in a Fourier series expansion. But before finding that, we will see what are these constants. A naught is equal to 1 by c into integral alpha to alpha plus 2c f of x dx. An is equal to 1 by c into integral alpha to alpha plus 2c f of x into cos n pi x by c dx. Similarly, bn is also equal to 1 by c into integral 0 to pi, alpha to alpha plus 2 pi, alpha to alpha plus 2 pi f of x into sin n pi x by c dx. This is what we have, and this is how we will be evaluating the coefficients, because this f of x is given in the question because you need to identify what's the function for which you need to write Fourier series expansion, and this is f of x value, where different constants can be evaluated by different integrals like this. Okay, so now in a special case where if the c is changing from within the interval 2 pi, means if the c value is pi, means the difference between these two intervals is 2 pi, then in that case you can put c is equal to pi in all these equations. Then if you put c is equal to pi here, if pi comes, this pi gets cancelled, so sigma n is equal to 1 to infinity an times cos nx plus, if you put c is equal to pi, then pi gets cancelled again, and sigma n is equal to 1 to infinity bn sin nx. Okay, similarly, if you put 2 pi here, pi here, in place of c you will be getting pi at all points. Means basically my intention is to tell you that this interval is defined over a length of 2c. So out of this 2c length, now if you are making this c value as pi, means if this interval is spread over 2 pi range, then in all these equations you should replace c with pi. Okay, that's what we have. So for Fourier series expansion of any function to exist, for Fourier series expansion of any function to exist, first condition, f of x should be finite valued, f of x should be finite valued, then it should be periodic. Next, 2, f of x should have a finite number of discontinuities, in given interval, like basically alpha to alpha plus 2c in given interval. Okay, and also if you see, this f of x should also have finite number of maxima and minima in given interval, and the function f of x should definitely satisfy all these conditions for the Fourier series expansion to exist. And these three conditions are called Distillate conditions, which are to be followed by any function for its Fourier series expansion to get valid. Okay, some issue is going on about S square sum. What is this S square sum? Okay, here it's A sin bt minus B sin AT. Correct? I think one minus sign we might have changed here. Is it? All of you, please say. If I take sin AT common, I'll be having A plus B plus A minus B. So 2 times of A divided by. So I think here A should come. Correct? A sin AT minus B sin BT. Is it? Okay, means 1 minus sign basically somewhere. I think here A should come and here B should come. That could solve our case. Correct? Because when we are simplifying the things, yeah, sin AT if you take common, 1 by A minus B minus 1 by A minus B. I mean, sorry, 1 by A minus B plus 1 by A plus B. So B gets cancelled and we'll be retaining A here and B here. Correct? I hope it's fine now. Just some minus sign cancellations and all these things you should take care. Okay. Then what about denominator? This is also A square minus B square again. Look, there is one minus sign that could come here. Okay. So I think this could be A square minus B square. Okay. Fine now. Some minus sign issues you should take care of, but this is the basic idea, okay, in evaluating the things. Clear to all of you? Okay. Just please take care of minus sign and all. Okay. I know you can simplify this thing from here. You can take sin AT common and you can perform some LCMs and all. You can work out the things. Okay. It's A square minus B square. See, we are not going to change this term anyhow. Please tell me this is A square minus B square or B square minus A square. One minus sign, I think it could have involved somewhere. Is this correct or B square minus A square? Please tell me, all of you. Do this calculation in a quiet way. B square minus A square. Okay. So this will retain as B square minus A square. Oh, it's correct. Okay, anyhow. Okay, now you decide whichever is correct. Fine. You can take one modulus sign common and now you can go for the things. A square minus B square is correct. Okay, so then fine. Okay, so see here. So this is basically the Distillate conditions which we need to clarify here. Okay, next we talked something about half range sine series and half range cosine series. Half range sine series and we'll discuss also something called half range cosine series. Okay, so normally why we call this as half range? Because the interval that we defined is alpha to alpha plus 2c, correct? Means we are assuming that this interval is of length 2c, but practically sometimes there could come a necessity for us. We need to evaluate the functions or the Fourier series expansions only in this interval, starting from 0 to c. Okay, like for example, if you are evaluating from 0 to c, means for example, if you take a string and this string is vibrating in a sine wave, then we start from the point x is equal to 0 to maybe this c is length of the string 0 to l. So sometimes it's not possible for us to continue from minus h to x, but from 0 to some limit value. So in that case, if this is the case, we write the half range Fourier series expansion. The half range sine series expansion, or you can write Fourier series expansion. Fourier series expansion of f of x in 0 to c. is given by f of x is equal to sigma n is equal to 1 to infinity bn into sin n pi x by c dx, where bn is equal to 2 by c into integral 0 to c f of x into sin n pi x by c dx. This is what you have. Okay, so bn is basically integral 2 by c into integral 0 to c f of x into sin n pi x by dx, and for this we have a big derivation which I am not of course going to deal with, but I want you to understand this formula. Okay, so basically you need to identify how to calculate this bn. So if you know this bn, you can get this expansion. Okay, so similarly, acha, dx is here actually, not here. Okay, because this is a series expansion. Okay, thank you Shankar. So here we have integration, so there is dx, but since this is just an expansion, we don't have any dx kind of thing here. Okay, similarly, and here normally when we are having 0 to c, we assume if you want to define half-range series of this f of x sine series from 0 to c, if the function is something like this f of x, we assume this to be minus f of x, means f of minus x is equal to minus f of x. This is what we assume from minus c to c, and we calculate for which we'll get these things as the answers. Okay, basically we make the odd function assumption because you know this sine function itself is a odd function. Next, for this, the half range cosine series, of cosine series, in a sense we of course deal with Fourier series only. So Fourier series expansion of f of x in 0 to c is given by f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity a n into cos n pi x divided by c. This is the Fourier series expansion. Yes, bn term won't be there in cosine series. So this is what we have, and this is half range sine series. So now the expressions for a naught and a n, if we calculate, a n is equal to 2 by c into integral 0 to c f of x dx. This is what you have, and a n is equal to 2 by c into integral 0 to c f of x into cos n pi x by c dx. So this is how you will be evaluating the half range cosine series formula for this and half range sine series formula for this as well. Okay. So basically this is how you'll be writing all these things. So half range sine series and half range cosine series. One time in GATE 2018, I guess, the question was something like this. The half range cosine series expansion of f of x is equal to cos square x in I guess 0 to 2 pi, for example, 2 pi interval is given by cos square x is equal to a naught plus sigma n is equal to 1 to infinity a n into cos nx, because it's given 0 to 2 pi, so directly they put cos nx here, because n pi x by c value is directly nx. So this is what they gave. The value of, I think they have given 2 also here, so kind people, so they gave 2. IIT Madras has organized in GATE 2019, and this question came in GATE 2019, I guess. Okay, so since RIIT is so kind, they gave this 2 also here. The value of A2 is dash. This is what the question they asked for. solution. So please solve and tell the answer. We have this function. Oh, today 42 likes. Good. Showing some mercy, yeah? Last class. Okay. Yes, for mechanical and civil, this 4 years is. For civil, I think there is no 4 years is. But once check anyhow. If you have, you can follow this. Okay. Anyhow, ESE and TVL people, I know 4 years is the heart of you. So please solve. This is the last question I'm going to solve in this course. Okay. So I want many of you to answer this. Look, even I thought this way. Actually, to be frank, in 2019, I don't know that this is in syllabus. 2018, I guess, something, 18 or 19, I don't bother. This is in syllabus or not. Now tell me one thing. Can I write cos square x as 1 plus cos 2x by 2? Yes or no? Can I write this? 1 by 2 plus half into cos 2x. So the coefficient of cos 2x is 1 by 2. Answer is 0.5. This is how I answered this in exam. Okay, because cos 2x can be written as 1 plus cos 2x divided by 2. So you know they're asking for coefficient of a2, means they want the coefficient of cos 2x. This is what we have. Okay, so answer is 0.5. Okay, you can perform proper calculations, you could get the answer 0.5 and all. So since this is a simple common sense, to be honest, in exam I don't remember the formula, but still we went for this. Okay, so sometimes I'm telling you again and again, in GATE exam they don't ask you for rocket science. Okay, they'll ask you for simple basics. You know, the name itself tells us GATE. This is aptitude. Okay, graduate aptitude means, you know, with the whole knowledge of engineering, what did the student learn? He should apply in a logical way. That's the only thing. Nothing beyond that. They don't ask some big rocket science derivations and all in GATE exam. They'll just ask you basics. But even though when they are asking basics, why only 18 out of 100 are qualifying is remaining 82 people, 82 people, they don't do calculations correctly like me. You have seen some calculation mistakes here and there. Second important thing is they don't have proper revision. They are all very intellectuals. Out of these 82, nearly definitely some more than 50 people will be very intellectuals. When I'm teaching, they'll solve the question by the time I write the ending of the question, and they'll tell the answer as soon as I start, as soon as I finish writing question. But they don't qualify GATE exam. Okay, this is because they don't have one important thing called revision in GATE exam. Okay, so in GATE, I'm telling you, for cracking GATE exam, you need not be very intellectual. Okay, if you work hard and if you have revision, means if you see, for example, I think today is the first time I used one paper to copy one question, correct, on board. But if you have complete, now for example, if I have complete maths in my mind, then you know at any moment if you ask me some question, I can answer at this moment. So something like this, if you have the knowledge of all the concepts on your fingertips, then this is really a very easy thing to deal with, GATE. And you know, many students, they keep preparing for GATE as long as possible, because one time if you score a rank below 500, that's it, your future is settled. Okay, so that's how. So Then I hope things are fine. Correct? Anyhow, I provided my contact to you already. So if there are some questions, you can talk to me at any time. So we can solve. Actually, you can try Suma. You will be getting 0.5. No issues. Okay. Because formulas or things give the same thing. Maybe some minus here and there. Clear? So, and then thank you all. Have a nice day. Anyhow, I think we'll be sending one feedback form as well. So you can sign that. Okay. Please make a calculation mistake. Acha, if you are using formula, you are getting 0. Then I think the question was something like this. The Fourier series of maybe. The Fourier series expansion of f of x. Okay, delete this half inch here. I don't remember the question actually, but the exact answer is 1/1.2. Okay, there can be a possible things where sigma this bn, basically bn into sine nx dx. I mean no dx. This bn can be 0 independent of the value of n. Okay, so definitely I think if this is Fourier series expansion, then you can get the answer easily. Okay, then integral 0 to 2 pi will be coming. So yeah, I think now you are applying minus pi to pi, correct? So that's why your answers are changing. So apply from 0 to 2 pi by taking as complete cosine Fourier series. Okay, so if I'm Fourier series, very less questions came for other branches like mechanical, civil and all. I want some 3-4 questions in these many years, but it's my responsibility to give you some data regarding the same. So things happen like this. So how did the course go on? I just want to know from you. Okay, later feedback forms and all. Okay, whatever they have, because you are the live audience right now. So I want you to know how the course went on over this past 45 days. I think, correct? Of course, we have some issues with the board and with some issues with panel, some issues with power cuts, internet issues and all. They sustained. Yeah, I agree. So apart from this, from my side, I think it's fine. Of course, anyone who teaches this feels it's fine from their side. So, okay. So I think it went fine. Okay. The main difference that it makes is if some engineer, if some engineering person teaches mathematics, then maths looks beautiful. Actually, that's what I feel personally, because wherever you have some chance to provide some nice explanations, you can provide it actually. Okay. So fine. Then I think I'll be sharing you some Google form to all the things that we are sharing this link, class link. We'll be getting some Google forms. You can always write there. And since you have my contact, whenever you have doubts, you can ask me. Okay. So in all students, all branches, you can ask me for maths questions. No problem. I'll answer you. For mechanical people, you can ask me questions from thermodynamics, applied thermodynamics, fluid mechanics, and strength of materials. From these 2 subjects, even civil people can ask me. We can answer to some extent. Okay. So yeah, I used to give mech examples a lot. Yeah, I agree, Monica, because to be honest, I don't know examples of other branches. But control systems is a common subject. That's why I know what are transfer functions, Nyquist plots, and all these things. But practically speaking, to be honest, I don't know any circuits or transistors and all these things. So, but mechanics is simple. 11th class physics examples is what I used, which is common to all of you. Okay. So some 11th class physics, for example, anything that we discussed here. Okay. So all of you, I wish you all a very good luck in GATE 2021. Okay. And I see all your photos when I come back to teach here again on the banners of Engineers Hub. Okay. With all your names that I'm seeing in the contacts now. Thank you all. Have a nice day. Thank you.